Okay, so today let's speak about the adjoint of matrix. Now, before we talk about the adjoint, I want to start with the convention for writing an element of a matrix. So, as I said, when matrices are discussed, when you put numbers, always the first number is the number of rows, and the second number is the number of columns, right? Let's say you have a 3 by 3 matrix, and you have therefore elements here and there and there. Let's say you have nine elements. Okay. Now, instead of calling all the elements A, B, C, D, E, a standard convention is to use 1, 1 for the first element, and 1, 2 for the second element. And let's think about what this A1, 2 might mean. It means this is an element in the first row, second column. Okay? As you can see, the first number indicates the row, the second number indicates the column. And then you have A1, 3. What would this be called then? A2, 1. Okay, and then A2, 2, A2, 3, then A3, 1, A3, 2, A3, 3. So that's the standard way elements of a matrix is addressed. And then I also denoted that there are these minor matrices, which is also denoted by capital A. It also has subscripts. So let's see, what is A, capital A1, 2? So this means it's the submatrix obtained by deleting this element, A1, 2, along with the same row and the same column. So what's left are these, right? So it's A2, 1, A2, 3, A3, 1, A3, 2. Okay, last time I introduced this as a matrix, and I treated this as a matrix before taking the determinant. But for today's discussion, I'll just say this is the determinant of this minor matrix. Yes?
Is it going to be A33 instead of 32?
Oh, thank you. So that's what this is called. It's a determinant of the minor matrix obtained by deleting a small a1, 2. So this is the determinant of minor matrix obtained by deleting first, for number 1, first row and second column. Okay. And then if you put different numbers, then this definition will be different. Okay? All right. So with this convention, now I can rewrite the determinant in a different way. I can say, for example, if I expand everything with respect to the first row, what would it look like? So first, A11, the checkerboard of signs should give you plus. Remember the checkerboard of signs is plus, minus, plus, minus, plus, minus, plus, minus, plus. And at A11, it's plus, I put plus. And then the submatrix, by deleting A11, is called capital A11, right? So this is really the determinant of this submatrix. And then the next element is A12. And here you can see that you can see that the checkerboard signs gives you minus, and I put A1. And then the last one is A13. Checkerboard of signs is plus. You have A1. Yes?
How come we put the A subscript 11, like the lowercase a subscript 11, instead of just uppercase a and 1?
No, okay, so, all right, so,
Like, what's the point of having both of them? I understand what they mean, but why
no. The actual definition of this, the determinant,
Yeah.
is you multiply A11 times A22, A23,
Oh, okay.
A32, A33, minus A12, A21, A23, A31, A33, plus A13, A21, A22, A31, A32. That's what this is, right? We learned this
Yeah.
when we were doing the determinant. All I'm saying is now I decide to call this as A11, call this as capital A12, this as capital A13. Okay? So everyone got it? Okay. So this is the new way I'm gonna call it. Although this is just, I'm just doing this so I can introduce this thing called adjoint. Whenever you're trying to compute the determinant, you're still going to use this one that we covered last time. Okay. I'm just doing this so that we understand what adjoints are. Now I'm ready to define what an adjoint of a matrix is. So definition. The adjoint of a matrix, not the determinant of a matrix, but the matrix itself. Adjoint of a matrix A11, A12, A13, A21, A22, A23, A31, A32, A33 is defined as, it's a new matrix out of the old, and it's defined like this. You just write capital A1, A11, A12, A13, A21, A22, A23, A31, A32, A33, and after doing this, you apply the checkerboard of signs. So you put plus, minus, plus, minus, plus, minus, plus, minus. Now,
So
yeah.
the checkerboard of signs only applied to 3 row and 3 column, or is it always applied to like?
oh yeah. I mean, if it's a 4x4, the definition will still can be applied because the next row will start with a minus, plus, minus, plus.
Okay.
Yeah. So you can, yeah.
So it still goes on.
Yeah. So I just wrote down the definition of a 3x3 matrix as adjoint, but it can be done for 4x4, 5x5, anything.
Okay.
Now, those of you who don't like these abstract definitions might want to see this actual thing. So let me show you how this is computed. So for example, if I want adjoint of, say, 102, 31, -1, 0, 5, 1. Let's say I want the adjoint of this. Well, this computing this is long and tedious, but let's try. So what do? I first want to figure out what goes here. What goes here? It's the determinant of this part, right? That's what it means because, as you can see, capital A11 means you delete this item along with the column and the row containing the item. So what's left is this much. Now, think about the determinant. What's that? 1 minus -5, that's positive 6, right? You put 6 there. Now, I go to the next element. I pick this element, and delete the row and the column containing it, and I get 3, -1, 0, 1. Compute the determinant, that's just 3, but the checkerboard of signs says I need to put a minus. So that minus comes from the checkerboard of signs. And then for this one, I choose 2. Deleting this thing gives you this matrix now, which is 3 times 5 minus 0, so that's 15. So that's what I write. And then you go on. Do I have to do the other ones? Pretty much understand what's going on now, right? Yeah, okay. So that's called the adjoint. So you do 6 more calculations, and that's called the adjoint. Do you need me to do the next ones? You want me to do the next one? Okay. 3, 1, 1. No, 3 is 0. Minus 10, but with the checkerboard sign says positive 10. So it's positive 10. 1, let's see, it's 1. Let's see, -1. Taking this away gives you 5. But with the minus because of the checkerboard of signs. It's -1. Picking this, I get 1, 2, 3, -1. 1 times -1 is -1 minus 6, -7. But the checkerboard of signs says I need to negate it, so it's positive 7. And picking up this, I get 1. Okay, so that's what this is. Yes?
For A31, it's
I made a
showing
mistake.
positive.
Let's see. A31. This is what I have, right? A31, this is capital A31. I need to take the determinant of this. 0 times -1 is 0. Oh, you're right. Yeah, so -2. And then, yeah, so it's -2. 1 times 2 is -2. The checkerboard of signs doesn't do anything else. Yeah.
And then if it's positive, you just go ahead and put positive.
No, this positive means you don't change the signs. This minus would change the sign, right? Yeah. If this thing is negative, then minus of that thing will be positive, right? If this thing is positive, minus of this thing will be negative, right? Okay. So that's the adjoint. All right. So what's the significance of the adjoint? Since I did so much work to get this, let's try to work with this. The significance of the adjoint, I'm going to explain why this happens. But it happens that if you sorry. There's one more thing I forgot. You need to take the transpose after this. And I forgot to explain to you what transpose is. Transpose is you leave the diagonal, that doesn't change, but you flip along the diagonal. So this becomes that, so these two change places, these two change places, these two change places. That's what transpose is. Okay, so let's do the transpose. So it's actually 3 steps, okay? Calculate the determinant of all the minor matrices, and then that's step 1. Step 2 is apply the checkerboard of signs, and step 3 is you transpose along the diagonal, and that's your adjoint. Okay? So you have, what was that? That's 6, 1, 1 doesn't change, but 10 and -3 switch places. -5 and 7 switch places. 15 and -2 switch places. So that's the adjoint. Okay. Now, what's going to happen is that if you have an adjoint of a matrix and you multiply the adjoint to the original matrix before you took the adjoint, if you multiply these two, the outcome will be a diagonal matrix where all the elements of the diagonal have the exact same value. And we can even predict what that value is. All right, so let me actually demonstrate that's true by multiplying this with that. Okay, so let's see. 1, 0, 2, 3, 1, negative 1, 0, 5, 1. Multiplied to 6, 10, negative 2, negative 3, 1, 7, 15, negative 5, 1. So if I didn't make any mistake, then this should be a diagonal matrix with the same number on the diagonal. This times this, that's 1 times 6, 0 times 3, that doesn't count. 2 times 15 is 30, 36. That's what I get. Right? Okay. This times this, 1 times 10 is 10, 2 times negative 5 is negative 10. 10 plus negative 10 is 0. See, it's already, you're seeing that off diagonal elements will be 0. You're only going to get the diagonal elements. This times this, okay. 1 times negative 2 is negative 2. 2 times 1 is positive 2. 0 times that doesn't count, so negative 2 plus positive 2, 0. All right, now let's go to the second row. This times that. 3 times 6 is 18. 1 times negative 3 is negative 3. Negative 1 times 15 is negative 15. 8, so we have 18 minus 3 minus 15, which is 0. This times that, 3 times 10, that's 30. 1 times 1 is 1. Negative 1 times negative 5 is 5. 5 plus 1 plus 30, 36. This times this, so 3 times negative 2 is negative 6. 1 times 7 is positive 7, so they add up to 1, but negative 1 times 1, that's negative 1. 1 plus negative 1 is 0. 0 times 6 is 0. 5 times negative 3 is negative 15. 1 times 15 is positive 15. Adding up may give you 0. 0 times 10 doesn't do anything. 5 times 1 is 5. 1 times negative 5 is negative 5. Adding 2, 0. And finally, if I do this, 5 times 7 is 35. 1 times 1 is 1. 1 plus 35 is 36. So you get the diagonal elements. And now let's think about why adjoint is a good thing. What does this achieve, having an adjoint? Do you have any idea what this is good for? Yeah? This is like 36 times identity, right? It's 36 times the identity. And therefore, what we're trying to say is that 1, 0, 2, 3, 1, negative 1, 0, 5, 1 times 1 over 36, 6, 10, negative 2, negative 3, 1, 7, 15, negative 5, 1 gives you the identity. Okay, so what can we say about this? What should we call this thing? No, this is the identity matrix.
The inverse?
It's the inverse of what? This matrix. Alright? Do you see how this thing works? I mean, I explained that it's desirable to have a formula for inverse matrix for 3 by 3 because when we were trying to solve system of equations using 2 by 2, it was awfully nice to have this formula for the inverse of a 2 by 2 matrix, right? Now, what are we getting? I mean, it is, of course, much more complicated, but we do see that if you have the adjoint, you're just one step away from having the identity. All right, so I need to explain to you two things. First, why does this happen? Okay? And then second, I will show you how to find the inverse of a 3 by 3 by using the adjoint. Okay? So that's what I'm about to do. Okay. first, think about the following. What are we doing? We are putting A11, A12, A13, A21, A22, A23, A31, A32, A33. I'm multiplying this by this thing called the adjoint, which is, let's copy this down over there, but we have to take the transpose. So let's see. The diagonals don't change, so it's A11, A22, A33. Those don't change, but these two switch places. So it's A12 here and A21 here with minuses. And here is A13 and there's A31. Those two switch places. And A23, A32 also switch places. So that's what we call the adjoint, right? This is the adjoint that I just wrote there. I'm trying to multiply with the original matrix. Now, think about what you would get if you multiplied across down. Let's just look at just this part. Okay? What do you get? A11 times A11, so you get A11 times capital A11. There's a minus, so the next one is negative A12 times capital A12. And then plus A13 times capital A13. What's this? What is this? Yeah, it's the determinant, right? I just erased this exact formula before I was writing this thing. Before I erased it, it was this exact thing. So this gives you the determinant. So what you're getting is this is the determinant of A11, A12, A13, A21, A22, A23, A31, A32. I mean, if you do a row expansion with the first one, you get exactly this. Now, then what about this times this? That will give you A11, A21 minus A12, A22 plus A13, A23. Now this time this is not a determinant, okay? In fact, only when you multiply the second row by the second column and third row by the third column, you're going to get the formula for the determinants. And that's why you're going to get the same number on the diagonals. So on the diagonals will be the determinant of the original matrix. Okay? That's what we figured out while I was trying to explain why this happens. Now, this is not the determinant of the original one. However, it's a determinant of something else. This is a determinant of let's see, A21. Right. So if you had A11, A12, A13, A11, A12, A13, A31, A32, A33, this would be the same as this one. If you took this matrix and expanded around here, you're going to get exactly this. In other words, this is a determinant of a matrix where you take the original matrix and replace the second column by the first one. So the first two columns are the same. Okay? And this is something that I haven't explained before, but it will turn out that whenever you have the same two rows or same two columns in a matrix, the determinant of that will always turn out to be 0. I should have explained this part before, but yeah. So that's my. So this is a little lacking because you don't fully understand this procedure, but I mean there's some reason why the off-diagonal elements will be 0, but this is easy to understand that the diagonal elements will be exactly the determinant. That you can fully understand, right? Yeah. Okay. So if you multiply these, the outcome will be that it will be the determinants on the diagonal and 0, 0, 0 everywhere. Okay. Where D is the determinant of the original thing. I'll call this as D. And therefore, we have a very good formula for finding an inverse of a matrix, because now you have A inverse equal to 1 over D, or 1 over the determinant of A, times the adjoint of A. That's the formula for the inverse. And this formula is actually applicable for all dimensions. Whether you have a 3 by 3, 4 by 4, or 5 by 5, you can always use this because adjoint is defined for any dimension. Okay? And you can always calculate matrices for higher dimensions. Yes?
Is adjoint A, is that one term or two terms?
Adjoint A is one matrix. It's a single matrix, which is defined by this. Okay. Yes?
We just switch it ourselves. Like to find adjacent A, we just switch the things ourselves. Let's find it.
Finding an adjoint of a given matrix
Yeah.
is 3 steps. First, find out all the determinants of the submatrix. Second, apply the signs, checkerboard of signs. Third, take the transpose. It has to be done in 3 steps.
What's it called, the transpose?
Transpose, yeah. Transpose is the diagonals are left intact,
Yeah.
but these off-diagonal elements, they change.